Hello everyone. So my thesis is about feasibility of duty cycling GPS receiver for trajectory-based services. As we all know, location information serves as a very important context to many smartphone applications. So among those location services, there are trajectory-based services which require continuous location traces. And we can imagine that it is very energy consuming. So in order to deal with this situation, we can ask some questions. Is such high sample rate really necessary? If we reduce the sample rate, can we still construct the routes from the GPS traces? So if we do so, which is the trade-off? Or what is the trade-off between the route accuracy and energy consumption? So first of all, let me talk about some backgrounds. The GPS system has 31 active satellites in orbit, and there is a set of ground management stations to monitor those satellites' status and orbits. In order to calculate position fix, the GPS receiver needs data transmitted from the satellite. So the data packet is as this one. As we can see here, there are 5 subframes in the GPS data frame. So the first one is clock correction data, and the second and third one is ephemeris data, which contains very precise information about the orbit of each satellite. And the fourth and the fifth subframes are automatic data, which contains coarse information about the status and orbit of the satellite. So a very important concept to understand GPS receiving is time to first fix. Time to first fix is the time that a GPS needs to spend in order to obtain a position fix. So the value of TTFF depends on GPS startup modes. There are 3 startup modes of GPS receiving. So the first one is cold start, which means the GPS receiver doesn't have a valid automatic data nor ephemeris data. So in order to calculate the location, the GPS receiver needs to search the whole space for satellites, and also it needs to decode the whole packet, which takes 30 seconds. The second startup mode is warm start, which means the GPS receiver has a valid automatic data, but it doesn't have ephemeris data. So under this condition, the GPS receiver doesn't need to decode the whole packet. It only needs to decode the clock correction data and ephemeris data. So under this condition, the TTFF is much faster. And the third startup mode is hot start, which means the GPS receiver has valid automatic data and ephemeris data. So the TTFF under this condition is usually 0.25 to 20 seconds, according to the national instrument. So after talking about the backgrounds, now we designed our experiments into 2 parts. The first part is experiments on GPS traces. So first of all, we need to collect the GPS traces, and then we can conduct the experiments on the GPS traces. The second part of the experiments is experiments on energy analysis. In order to do so, first of all, we need to analyze the GPS TTFF. And after that, we can measure the battery consumption of the GPS device. And in the combination of the 2 parts, we can have the trade-off between the energy consumption and the route accuracy. So the purpose of data collection is to collect real-life driving GPS traces. So the GPS traces we collected has the format as time-stamped latitude and longitude coordinates. Totally, we collected 123 traces, and the total distance of the traces is 1,188 miles. The sample rate of it is 1 Hz. So this is how we conducted the experiments on GPS traces. First of all, we have the original traces sampled at 1 Hz, and after constructing the path of it, we have the correct route. And to simulate reducing sample rates, we remove the nodes from the original traces so that we can get traces with reduced sample rate here. So after construct the path from all of those traces, we compare those routes with the correct routes so that we can evaluate the route accuracy. So the map matching is the first step to deal with the GPS traces. Here we have the location samples from the GPS traces, and we have the map data. And in order to get the trajectory, we need to match those location samples onto the map data.
Well, that was quite fast.
So,
any more details on that process?
Yeah. So the map data we used is from the OpenStreetMap. Each node in the OpenStreetMap has its unique node ID and latitude and longitude coordinates. And each road on the map has its own unique VID, name, type, node IDs of all the nodes on it. And there is a adjacencies table to describe connectivity among those nodes on a certain road. So there is a speed type table to describe the speed limit for each road type.
So what is this OpenStreetMap? Is that it's a public tool that's available?
It's actually a public project online.
Okay. So it has lots of roads information.
Yeah, right. So users collect those data and then upload onto the website.
Very good. Do they also have the access points on each road, those information?
Yeah, they have.
Oh, okay. That might be useful for the other part.
So the map matching is very difficult. It's very difficult because of the noise of the GPS trace. As we can see here, those red nodes represent the trajectory, and this black node is actually from the GPS trace. And all we need to do is match the black node onto the map data. So the blue node is actually the closest node to the black node in the map data. As we can see here, if we match the black node, simply match it onto the closest node in the database, we get a wrong node, which is the blue one. So in order to do that, we have a new approach that we didn't just think about the distance to the black node in the database. We also think about the connectivity among those nodes, so that we can get a better performance. So then there is a path constructing problem. This is the most important part in our algorithm. So the path constructing problem has two scenarios. This is the first one. The first one is if the two nodes have same VID, meaning they are actually on the same road. So we want to construct the path from this scenario. All we need to do is just simply connect the two nodes by adding some points between them along the road. So the second scenario of path constructing problem is when two nodes have different VIDs, meaning they are on different roads, this one and this one. So in order to construct paths from this scenario, we need to explore possible paths between them by using breadth first search, so that we can find the most likely path between them. So after constructing the path, we need to evaluate the routes we constructed. So this is how we do it. First of all, we have the correct route, the below one. And then we have the matched route, the upper one. And we use D0 to denote the length of a correct route, and D- to denote the length erroneously subtracted, and D+ to denote the length erroneously added. So we can evaluate the accuracy by mismatched fraction of root, denoted by D+ plus D- to D0. So this is one of example of single GPS traces. As we can see here, the density of the GPS traces, the density of the GPS trace is pretty high. And after map matching, we have the trajectory on the digital map. As you can see here, actually the density of the trajectory is not as high as the original trace, which proves that sampling at 1 Hz is not necessary. So after constructing the path from traces with reduced sample rate, we have the result here. We may notice that the 50-second sample period trace has even a better result than the 30-second one. So this is what happened here. As we can see, after reducing the sample rate, there are only 10 nodes remaining in the 30-second sample period trace. So after constructing paths, we have the result here. And in comparison with the correct route, which is this one, and we notice that there is mismatched fraction of route. So this is the 50-second sample period trace, which has only 6 nodes left. And after constructing the path from it, we have the path here, we have the route here. And in comparison with the correct route, we know that it's 100% correct. So to further explain what happened, we have the figure here. As we can see here, even though the density of nodes in the 30-second sample period is higher than the 50-second sample period trace, it actually misses the one key node on the curvy road. And it's a nature of EFS that when we constructing paths between the two nodes, we turn to find the shortest path between them, which gives us a wrong path in this case. So after running our program on all the traces, we have the result here. So as we can see here, the mismatched fraction of root is generally increasing as the sample period increases. And the maximum slope happens when the sample period is at 20 seconds to 40 seconds. And when the sample period increases to 120 seconds here, the mismatched fraction of root actually doesn't change much. You can see here, from 2 minutes to 5 minutes, it doesn't change much. It turns to be stable at 0.23 to 0.25. So in comparison with the length of the period, the loss of accuracy is not that much. So now we have the second part of the experiments, which is energy analysis. In order to do so, first of all, we need to run some tests on GPS TTFF. So we tested
What's
GPS.
TTFF?
time to first fix.
Okay.
Yeah, which means the GPS receiver, the time GPS receiver needs to spend in order to obtain a position fix. So we run the test under normal driving condition, and the GPS receiver performs false start each time. And totally we collected 1,150 samples. So this is how they distributed. And we can see the probability that it takes less than 20 seconds to get a position fix is more than 94%, which satisfies the data provided by National Instrument. And the average of the GPS...
What is National Instrument?
National Instruments Company.
Okay.
Yeah, this data is actually in the white paper provided by National Instrument.
Borrow.
So the average of GPS TTFF from our experiments is 11.55 seconds, with a standard deviation of 6.63 seconds. As we can see here, the peak is actually pretty narrow. So we conducted our battery consumption experiment as this one. So first of all, we have the smartphone, which is on sleep mode, and run a background service to turn on the GPS receiver. And we have a resistor of 0.5 ohm in series with the circuit. And we use the oscilloscope to measure the voltage drop on the resistor, so that we can get the current of the circuit. So we have the current of the circuit, and we have the voltage of the device. Then we have the energy consumption. So the power consumption on sleep mode is 29.6 millivolts. And the power consumption on sampling is millivolts.
On sleep?
Yeah.
Really?
That's pretty high.
Yeah, it is.
Watts is power, by the way.
Yeah. There is some noise on the oscilloscope actually when I do it.
Okay.
And the energy consumption on sampling is 325.6 millivolts.
So usually there's a huge difference between sleep mode and active mode. So here I'm not familiar with this device, but I may be wrong.
So which sleep mode was this now? Are you referring GPS sleep or?
Actually, the sleep mode is actually the smartphone do nothing.
That's not sleep mode, that's idling.
Idling.
Oh, okay. That's different.
Okay, so it means the CPU is still running, etc.
Right.
Right. Okay. Good.
And when you say energy consumption, you really mean power consumption.
Consumption, yeah.
Right.
So we have the trade-off analysis summarized as the equation. So the total duration is actually the time interval between samples, between the GPS samples. This is actually the GPS sample period in the experiments on GPS traces. And we have the T-off and T-on. The T-off is the time that the GPS receiver has been off during each cycle. And T-on is the time that GPS receiver has been on during each cycle. So the power consumption of duty cycling GPS can be calculated by continuous GPS sampling power consumption and power consumption of sleep mode. So we have we set the T-on as the average value of GPS TTFI, which is 11.55 seconds. And we have the result here in the combination of the first part of the experiments. So this is how does it look like in the chart.
Well, don't speak that fast. Explain it a bit.
What are the axes?
So as we can see here,
What are the axes?
well, the x-axis is the sample period. Yeah, and this y-axis is actually the power consumption here, and the unit with unit millivolts. And the mismatched fraction is colored by blue here. So
what do we learn from this figure?
well, as we can see, as the sample period increases, the power consumption drops very fast, and the power consumption is actually the mismatched fraction of root is actually generally increasing, and the maximum slope happens here. And after 120 seconds, it's actually not changed that much, and it turns to be stable at 0.23 to 0.25. So this can be related to the composition of each root, because during the root we have the highway part and the local parts. So in the local parts there are more rows, and the density of the rows are really high. So and in the highway parts actually we don't have such high density of rows. So when we construct the paths, the chance of we choose a wrong path is actually higher on the local parts than the highway parts.
Your power consumption only measuring the draw from the GPS unit?
Yeah,
Okay.
that's true.
So if you were to set your x-axis to infinity, you would expect that the red curve would go to 0 then, not some baseline minimal power draw.
Well, the baseline of the power consumption is the sleep mode.
But you're only measuring the GPS.
Well,
Yeah.
can't measure only the GPS.
Right, so that's my question.
Right.
So, all right, there is some baseline then.
Yeah, there is some baseline. The baseline is actually the sleep mode.
Mm-hmm.
Yeah, when they put the smartphone on the sleep. So now we can draw the conclusions. So as we can see here, the continuous GPS sampling with sample rate of 1 Hz is not necessary even for trajectory-based services. As we can recall, the density of the trajectory is not as high as the original GPS trace. And duty cycling GPS receiver can save considerable energy without much loss of route accuracy. So as we can recall here.
What was the velocity of your vehicle during the study?
Well, under normal condition, just the speed limit, I guess.
I mean, normal conditions, anything
Yeah.
less than the speed of light, right? So,
So we have so many participants in this experiments. So everyone just carry a smartphone and collect the data on the road. So
There's also a thing of if you drive fast, that means the distracting roads will be fewer. So there's this rough correlation there. If you drive slow, but it might be local roads, then you will have lots of distractions. So that in that case, maybe the impact of velocity will sort of be cancelled out.
Right, so the faster you can drive, the less you need to sample. Almost.
right. I'm just trying to say,
Because it's highway. Right?
once a second,
But that's something
is not that important if I'm walking down the street.
Yeah, it's something you need to discuss. You better discuss, right? Because otherwise, it's a little bit
You
vague.
don't have to discuss, but it just should be aware of.
So after the study, we can see the duty cycle based on the trade-off analysis. So for example, For example, we want to control the mismatched fraction of routes maybe under 0.20. So we can only schedule the duty cycle less than 30 seconds. So we know that the tolerance of reducing sample rate is different to highway and local roads of the route. So when we think about future works, we can actually analyze the parameter of local roads and highway. Maybe there is a speed limit, and maybe there is a density of roads, and we can summarize those parameters to get a better performance. So that's it.
Okay, let's back